but that's okay. I'm normally that confused. What I'm trying to talk about is, from whence cometh all these various waters that we're trying to see. Having been a lunatic from way back, I was one of the ones who was against lunar water, pretty much, and now I'm 100% for it. And we've seen things change such that we have this type of image, water on the moon. What I'm going to talk about today is long ago up to today, and the endo versus the exogenic type of water. The effectively the bone dry, where it used to be, up to now we effectively have lunar mare, and rust to glaciers, nanophase iron to glutamates. Then I'll be focusing in primarily on the endogenic. In other words, the samples, the lunar samples that are magmatic. And I'll go from apatite, starting with Francis McCubbin, and then move into Albertus and all the great work that's being done, and then many more things that are coming along the line. I just can't help but giving praise to Carly's team here that found the first evidence for water on the moon, and it was supported by two of our team members, Roger Clark and Jessica Sunshine. And we came up with this whole idea of this solar wind hydrogen and forming some of this potential OH on the moon. And we had this, a naive way of saying it. I was looking to make dangling bonds somehow, so I come up with this crushing and shattering, much the same as what a geologist beats on a rock. You have a strange smell that's given off. It's activated surfaces. And we have these activated surfaces reacting with the OH, with the hydrogen coming along from the solar wind to form OH and maybe HOH. And this was what Carly called her space dew. Now, then we had this thing. This will come along. We're going to have a talk tomorrow by Andrew Ishimura. He is the first author on this paper, in which we performed OD and OH from bombardment of lunar soil. And we did the OD because we had a bit of a compromise in bringing our sample into the air for a moment. And he'll talk some more about that tomorrow. And then the big thing that happened right after we made our announcement was L-Cross. And Tony's going to give you a whole big spiel about that. I'm anxious to hear what the latest thing is. I would really like to know all the various chemicals that have been found in their abundances. I've heard that the amount of volatile given off at Cabeus, which wasn't what we thought it might be, seems to have grown over the last couple of years. We'll hear from Tony about that. And commentary has got all sorts of things in it. We'll hear how perhaps some of the OH that we're seeing with Carly's, with the remote sensing, is actually hip-hopping to the poles and is adding a bit of another exogenic flavor to it. This is what we had back in 1973. We had goethite. We had this rust. We're still going around about rust. Chip Scherer's writing a paper about the rust and the rusty rock and how it got there. And I was one of the first ones who say that it wasn't actually rust, and we had identified it as academia, and that it was terrestrial contamination. And having a big enough mouth, I just sort of overwhelmed people, and we forgot all about the fact that there might be lunar water for too long. And then, to contrast to that, 37 years later, we have people with Paul Sputis and his cellmates, and then they come up with this whole idea that 40 craters in the North Pole had just a tiny bit of water, just 600 million tons. So we're going from being almost nothing to having too much. And then along the way, we were looking at the fact that how did this nanophase iron form? Back in the 70s, it took us 3 years to figure out any possible mode of formation from this nanophase iron. The one we came up with was one postulated by Bob Housley, and it was a solar wind reduction of, in other words, a solar wind has penetrated the soil, the surface of every grain, and then when you heat this up during impact melting, the FeO breaks its bonds very easily to form water. And this was a pretty good idea, and this is what prevailed until the 90s, until Dave McKay and Lindsay Keller came along and sort of came up with a really proof in the pudding type of measurement. So what we did is we looked at the glutamate blasts, where they were wondering about it. Back in '95, I did this with George Rossman, and we didn't quite find much in the way of signal. But then again, it's probably the fact that I didn't prepare the samples as well as I should have. But then when Yang did this, Yang Lu, she found 150 parts per million of water in one part, 200, 120, and actually larger amounts. And we also did this, it was confirmed by SIMS, and when we did SIMS, we came up with something that we'll see later that Lu has come up with, and that is nominally anhydrous minerals also contain some water. So we're left with this big quandary about all this different forms of water that we're seeing on the moon. We've got solar wind reduction, we've got solar wind implantation, we've got stuff, of course, that comes from comets and meteorites, and that's what we think is a major input to the polar ice. And then we got magmatic samples, and we don't know really what part that plays in the whole thing. But these are, for us, for petrologists, are the most important things, because these are the things that speak to the whole formation of the moon. And this is the thing I'm going to talk about, go into detail now. Back in Apollo times, we had this mineral apatite. Apatite is a calcium phosphate. It was important back then because it was a source of uranium thorium. And so Wasserberg and all those guys, everyone wanted to know about the apatite that was in there, mainly for the amount of apatite, not so much for its chemistry as far as the major elements, but the uranium thorium. And we also always suspected that there might be a little bit OH in there because we didn't satisfy the charge balance. And we sort of let that go for too many years. And then Francis McCubbin jumped on it and started making a big to-do about it, and actually carefully measured fluorine, and then by summation came up with an OH content for various rocks. And this was the beginning of our chase after apatites. And just to show you one, not that I'm a little bit prejudiced, but I'll show you what we did. This is the late-stage mesostasis that we have in almost all of the lunar basalts. It's almost a late-stage creep. It duplicates the lunar magma ocean to some extent. And lo and behold, we have various things. Our glass contains potassium, barium, but we have this apatite. And this apatite here has 1,600 parts per million water. And this was what we first found reported in the Lunar Planetary Science Conference with the Caltech group. And then this resulted in a paper by Jeremy Boyce a year later, or later on that year. So we have direct confirmation of water in all sorts of apatites. Jim Greenwood, with his Japanese cohorts, went after this, and they found water there in different papers. They finally published one paper in 2012. I was in on this, trying to give him some advice on sections and stuff like that to use. Francis was doing a fantastic job, and he publishes. He was the first one to publish it. He got put in the Proceedings of the National Academy of Science. We had this paper by Yang, which was just an abstract. But then Jeremy Boyce, we redid all the work that was done at Caltech, and Jeremy published in Nature in 2010. But we found, we're starting out not just talk about parts per million. We talk about, 12,000 parts per million, 15,000 parts per million. We're finding all sorts of water all over the place. So it sort of justifies that lake that we had in the first slide. Then when we got to this stage, we're trying to interpret, and this is where we're having problems all along, is interpretation of what the D to H ratios are. And this, in the lower right, shows you what a D to H ratio is for delta D. And on this plot, we have all these different ones from just a paper with Jim Greenwood that I was also on. And we came to the conclusion that probably this was cometary water. Now, you'll notice the ones in blue here in the middle, the 1239. We have all these different values, different delta Ds, and different water contents. And so we're confusing. What does one sample mean? Suppose I only do one analysis of one sample. If we do multiple analysis of one single apatite, we can also get a variance. So we've got something that's the tail end of crystallization that's trying to tell us something, but we're not able to read it. We don't get as much of variance as other rocks, 12040, 14053, a very highly reduced rock, and not really a good one for use for an example, but it had something which was near Earth pretty much in its water content. And in order to account for this strange cometary input, we came up with this type of scenario where we had, our Stevenson and Company's great idea about the formation, the giant impact, and then we put the moons out here, and we put a few comets around. Now, the comets were hitting the Earth, they're hitting the moon, but the same flux doesn't make much difference to the Earth, but it does to the moon. So we could account for this cometary water input on the moon. And so that's where we stood then. And then we have our next thing that comes along, and this is Albertus. And this is the first real lunar sample that was unequivocally a good sample to use, and it was the orange soil and the green soil, Apollo 15, Apollo 17. This is the orange soil from Jack's 74220, Jack Schmidt's 74220, and they found, in the 40 percentile, 40 ppm range, and then they theorized that there was a diffusion of hydrogen when the samples were still hot, and so they took this and they, effectively worked it up to a factor of 10, which was the original part. And so we had, some really good evidence now out of samples that were not from the last formation of magma. These were from the early formation of the magma. And then we're joined by Eric Howley. Basically, it's Albertus team out of Brown with Eric Howley at DTM. And with Eric, with his, micro SEM or micro SIMs, was able to look at melt inclusions of basaltic olivine, and he was finding even more quantity. But again, we didn't go too far with the interpretation yet. And then to bring us up to 2013, all of a sudden we had a rash of new papers. We had one with Yang Liu in 2012, which was about the really first evidence for OH being the FTIR we did on lunar samples. But here we have one from Mahesh's group in Open University, and some really fine work. And what I liked about this is that they took into consideration the various types of processes that would affect the samples, the partial melting of the mantle first in order to derive our magma, transportation to the surface, degassing, or fractional crystallization. And they were able to account for most of the values that they had in the high titanium, low titanium basalts with these types of techniques. And it was, to me, was really good attempt at modeling. And the one we came up with, they said, was it had a chondritic flavor. Now, chondritic flavor, they didn't go as far as to say, hey, this is the same as the Earth. But chondritic and the Earth are getting pretty darn close together. Then we had another situation, which was basically taking the magma ocean idea and saying, okay, and this is by who? This is Clive Neal's group at Notre Dame. And they said, yes, we could find 6 parts per million, only 6 parts per million. That's quite a bit for a plagioclase now. These are nominally anhydrous minerals, are NAMs. Okay, this is what Yang had found. This is what Hu has found. And then they took this, and this is a bit of stretch. And this is Clive, as far as I'm concerned. And it stretched from there, it stretched by a factor of 60 to what the initial lunar magma ocean is. And again, these are speculations, but we're going after trying to recreate the situation that formed the moon. And then all the way to 14,000, 1.4 weight percent water in the Earth Creep, the last formation of the lunar magma ocean. And this is something like, yeah.
Larry, you have 4 minutes left, which means 2 minutes till question time.
Okay, fine. Okay, so this was a good start at what we have in the lunar magma ocean, and this is just John Wood, who was one of the ones who came up with this way back when. And then we move ahead to a couple weeks ago. Albertus is back on track again with his group, with Eric from DTM and the rest of his cohorts at Brown University. And they're looking at both the soils, the glasses, and they're looking at the melt inclusions in olivine. And they came up with this. Now, you'll see that it's a multi-log unit times a multi-log unit, which is great for bringing everything together. It's not a log to the base 10, so it's not quite as bad as it may seem. But in fact, the carbonaceous chondrites that they have measured, that we know about, and the values that they've measured for the moon all seem to group together in this same thing. Now, I'll point out that what Mahesh had done in Romaine, published in January, that was basically, you could throw in chondrites in here as well. So they're saying, hey, they're all the same, and so the Earth and the Moon may have a lot more in common than we ever thought. And this is, Mahesh didn't mention it, but the fact is that was something that could have come out of their analysis as well. And I'm sort of lost at this stage. I don't know where to go from here. It's going to affect Dave Stevenson's ideas on modeling. How do we come up with something which is a homogeneous moon and Earth, which have the same basic water contents, oxygen isotopes and everything? Maybe the moon is a split off the Earth. Various things that we can come up with. Which leaves me with water on the moon, water in the moon, and a whole lot of questions that I don't know. We're tackling them slowly but surely. In the last 2-3 years, we've made fantastic progress into modeling this. Albertus' paper just a couple of days ago got fantastic coverage. It's all over the world, and I applaud that. But again, we're all guilty of this as scientists. We have a way of jumping to glory a little bit too quick. And there's a lot of work to be done. And I'll close with that saying that we've just started to scratch the surface of the lunar water situation and how it relates to the Earth. And thank you very much for your kind attention. And I didn't hear any applause, but I assume you applaud.
Thank you so much, Larry. Okay, Dana, take it away.
All right, well, Carly, if you're on, and if anybody has some questions, please type them into the chat window, and we'll read them off and give Larry the chance to answer them.
Do we have any questions yet?
Yeah, or if people who are on video raise their hand, we can call on them.
Well, I kept it right on time, so.
You did. Thank you so much.
Well, and also, Larry, a lot of the things you referred to really set the stage for the next several sessions. Many of the people that you referenced, I hope, will give an update of just the items that you highlighted. So this is just the beginning. Thank you for bringing everyone in and setting the stage.
Okay, well, set the stage for you too, Carl. Go ahead.
Yeah, so our next speaker